In lecture 8, we have discussed CSTRs in series and also plug flow reactors in series. Welcome to chapter 9, where we're going to discuss combinations of CSTRs and plug flow reactors in series. The final sequences we shall consider are combinations of CSTRs and plug flow reactors in series. We have here an industrial example where we have two CSTRs, as you can see here, so they are well mixed, okay, followed by plug flow reactors in series, as you can see it there, where you have long tubes. This sequence is used to dimerize, so it's not polymerize, it's dimerize. So you're bringing together two molecules to dimerize propylene into isohexenes. Example of dimerizing propylene. See here we have 1 carbon, 2 carbon, 3 carbons. So they are propene or propylene because you have here double bond. Okay, and you are turning it, so you have two molecules of this, that's why we are dimerizing, and you are converting it into isohexene. So you have 1, 2, 3 carbon molecules atoms, and now here we have 6, 1, 2, 3, 4, 5, 6, and it's in the iso configuration because this carbon, as you can see, is connected to 3 other carbon atoms. So that's the dimerization. A schematic of the industrial reactor is shown here. Of course, this is a CSTR, right? And this is a CSTR as well, while this is a plug flow reactor. This is a schematic diagram of the real reactive system. Okay, so let's write the design equation for each reactor in the shown reactor system. Okay, so the first one is CSTR. What would be the design equation? Well, the design equation would be V1, correct? So I'm concerned with reactor 1, which has a volume of V1. So V1 equals, this is a CSTR, so we have algebraic equation. So let's see. We have reactor 1, so it will be FA naught divided by minus RA1, that is the rate of reaction inside reactor 1, right, times X1. So that's the design equation for the first reactor. And of course, we have here reactor in series with no side stream, so all our calculation, all our conversions are based on the feed to the first reactor. So let's write the second design equation, or the design equation for the second reactor, where we have reactor 2. So therefore, we are interested in V2. So V2 equals, again, FA naught, or our calculation, or our conversion based on the feed to the first reactor divided by minus RA2, of course, because we are talking about the rate of reaction inside reactor 2. That's what V2 is function of. Of course, it's not going to achieve the whole conversion of X2, right? It's going to achieve the difference, X2 minus X1. And finally, we're going to write the design equation for the third reactor. This is the third reactor, so we are interested in V3. So V3 here, this is we have an integral form of the design equation, correct? It's not algebraic form. Okay, so integration of, again, FA naught, because all our calculation conversion based on the feed to the first reactor. Okay, so FA naught divided by minus RA Okay, and I'm not gonna write minus RA3 because I'm afraid if I wrote this, you might think this is the rate at this point, at the exit, which is not true. I'm not interested in the rate at the exit. Here the rate is changing as you go down the length of the reactor, so I'm going to leave it as a variable minus RA times dx. Okay, but how or from where to where we evaluate minus RA? Well, we evaluate it when x equals x2 all the way to x3. Okay, so now we know how to write the design equations as explained. Type. Assume that the presented dimerization reaction follows the same kinetics as that of the previously discussed isomerization reaction. So just take the same kinetic. Shade the area and the Levin-Hb plot that would give the volume of each of the shown reactors that are responsible to achieve x1.4, x2.6, x3.8. So let's shade the areas. Let's start with V1. Well, V1, volume 1 is for the CSTR, so it's the area of a rectangle, right? You have to always look at the design equation, and the conversion is taking me up to 0.4. So that's the width, right? And what's the height? The height is evaluated at the exit, right? Okay, so that's the width, the height. So the width times the height gives you this, right? Obviously, because the design equation was V1 equal if A naught divided by minus RA evaluated at the exit multiplied by x1. So this is the width and this is the height evaluated at the exit at x1. Okay, let's look at the second reactor. Okay, let's write it down. Okay, second reactor. The area representing the volume of the second reactor, we said it's if A naught over minus RA2 multiplied by x2 minus x1. So the width now is x2 minus x1. What is x2? It's 0.6 minus 0.6 minus 0.4. So this is the width then. Okay, this is the width. What's the height? Is it evaluated at 0.4 or at 0.6? Well, it's evaluated at 0.6 because this 0.6, conversion of 0.6 represents the concentration, right, at the exit of reactor 2. Concentration here, which is similar to the concentration here, right, which helps you to evaluate minus RA2. Okay, so that's the width, x2 minus x1, and we say the height is evaluated at x2, so this is the height. So therefore this is the rectangle. Okay, let's look at the last design equation, which is V3 equals, let me say, the integration of f A naught over minus RA times dx from x2 to x3. So now this is the area under the curve from x2, which is 0.6, all the way to x3, which is 0.8. Okay, so here we go. Evaluation will be from here to here, and it is the area under the curve. Okay, excellent شباب. طيب, combination of CSTRs and series, and let's learn more. The minus RA versus X data and the Levin-Hb plot we have been using in the previous examples are typical of those found in isothermal reaction system. Why are we saying typical examples for isothermal reactions? Well, because the rate of reaction is a function of mainly two variables, temperature and concentration. The temperature is constant, isothermal operation, so the rate of reaction here is a function of concentration. And as the reaction progresses, as known from the conversion as followed followed by the conversion. As the reaction progresses, the concentration decreases. Therefore, the rate of reaction decreases as well, right? Or 1 over minus RA increases. So that's so typical for isothermal reactions, where its rate, of course, is not zero order. We will now consider a real reaction system that is carried out adiabatically. What does adiabatic mean? Well, it means there is no heat transfer, right? There is no heat transfer between your reactor and the environment and the surrounding. Isothermal reaction systems are discussed in Chapter 4 and designed in Chapter 4, while adiabatic systems in Chapter 8. Example 2.7. An adiabatic liquid-phase isomerization. The isomerization of butane from normal butane to isobutane was carried out adiabatically in the liquid phase, and the following data were obtained. So that's the data we have. Note: minus RA behaves differently compared to minus RA of isothermal reaction. Is that true? Well, let's see. As the reaction progresses, see the conversion increasing, what happens to the rate of reaction? The rate of reaction does not decrease, it increases, right? It increases. Then it decreases. So it's unlike the data we have seen earlier. So what's the reason of this? Any idea? Well, it's not magic, right? Anymore. You know the science. You can explain anything. You want to explain the rate of reaction? What do you look at? You look at the variables affecting the rate of reaction. What are these variables? Temperature and concentration. For the adiabatic operation, is the temperature constant? Well, it cannot be constant, because when you have a reaction, and let's say this reaction is exothermic, so it's releasing energy, right? And this energy, can it leave the system? Can this energy released from the reaction, okay, can it leave the system? Of course not, right? It cannot leave the system. Why? Because the reactor is insulated and the operation is adiabatic, no heat transfer. So this heat stays within the system. What happens? What does it do to the system? It will increase the energy of the system, and therefore you'll see the temperature gauge going up, right? Temperature gauge is going up. Okay, so it will increase the temperature inside the system. Let's take an example of endothermic reaction. For an endothermic reaction, the reaction absorbs heat. So if the reaction is absorbing heat, okay, so the reaction is absorbing heat, can we supply this amount of heat needed from outside? No, we can't. The system is insulated. So where does it take heat from? It takes heat from within, from itself. And when it takes heat from itself, its temperature decreases. So you see that the temperature gauge goes down. Okay, so for an adiabatic reactive system, yeah, you see that the temperature has to change. Okay. Okay, great. So that's regarding temperature. What about the concentration? Well, as the reaction progresses, whether you have exothermic reaction or endothermic reaction, so long the reaction is progressing, the conversion is increasing, the concentration decreases. So now let's explain what's happening here. Okay, so we know that the rate of reaction is function of temperature and concentration. So here we have A is going to B, okay, for this reversible reaction. Okay, so it's a reversible reaction. Of course, the rate of reaction is function of both concentration of A and B. Okay, as the reaction progresses, the temperature increases, right? From the beginning to the end. Okay, so far that the reaction is going forward. Okay, there is chances of heat being released if the reaction was exothermic, or there are chances that the temperature will decrease, or I shouldn't say chances, it will happen. If the reaction is exothermic, the temperature increases as the reaction progresses. If the reaction was endothermic, the temperature decreases. Okay, but in this case, in this specific case here we're talking about, we see that the rate of reaction is increasing, despite that the concentration of A is decreasing and concentration of B is increasing. So that means if the rate of reaction is increasing, that means the temperature must be increasing. Temperature must be increasing. That's why the rate of reaction is increasing. Okay, so let me say it again. The rate of reaction is function of temperature and concentration. As the reaction progresses, for this specific reaction, heat is being released, okay, because now we know that the reaction must be exothermic. Heat is released, and therefore temperature is increasing. So as the reaction progresses, temperature increases, which affects the rate of reaction positively, meaning it will try to increase the rate of reaction. On the other hand, as the reaction progresses, as conversion increases, right, the concentration of A decreases while the concentration of B increases, which affects the rate of reaction negatively, right? Okay, let's make it clearer. If you recall from applied physical chemistry, we can write, if this reaction was an isothermal, an elementary reaction, then the rate will be K times Ca minus Cb divided by Kc, right? And you can see that if Ca decreases, the rate decreases, or if Cb increases, the rate also decreases. So as the reaction progresses, the concentration of A decreases and the concentration of B increases, which affects the rate of reaction negatively. So now you have two forces here acting in your rate of reaction as the reaction progresses. Okay, as the reaction progresses to whatever x. Okay, what are these? This is temperature increasing, which affects the rate of reaction positively, and then you have the concentration change, right? Concentration change, which affects the rate of reaction negatively. So someone is pulling up, the other guy is pulling down. Who wins? Let's see who wins. Apparently, at the beginning of the reaction, okay, as the reaction progresses, we have the effect of the increase in temperature on the rate of reaction is more than the effect of the change in concentration. Therefore, the rate of reaction increases. Okay, so it keeps increasing until it reaches a maximum value at a conversion of 0.4. However, further progress of the reaction will cause the rate of reaction to decrease, because now the effect of the increase in temperature is less pronounced than the effect of the change in concentration. So now the change in concentration has more effect on the rate of reaction than the increase in temperature on the rate of reaction. And as we know, as the concentration changes, the rate of reaction will decrease. Okay, so now we have this explanation explaining the behavior of the rate of reaction. So in conclusion, some parameter pulling the rate of reaction up, the other one is pulling the rate of reaction down. The question is, who will win? Okay. Okay. And the second point I wanted to discuss, that this is a real data for a real reaction that was carried out again adiabatically. طيب, so let's summarize one more time how the rate of reaction is changing. So let's plot the variables against x, and let's say x here is 0 and x here is 0.4. Okay, and let's say x here is 0.65. Okay, and let's see what's happening to conversion. So obviously, as the reaction is progressing, conversion is increasing, correct? Conversion is increasing, as you can see. Okay, so if you want to, yeah, it's useless to plot x versus x, but if you want to plot it, it will be something like that, right? As the reaction progresses, x increasing, so it's increasing. Okay, but let's see what happens to the concentration of A. Concentration, as the reaction is progressing, the concentration of A will drop, correct? It will drop. Okay, so this is concentration of A. What happens to concentration of B? It increases as the reaction progresses, right? Okay, this is concentration of B. What happens to the temperature? Well, for the temperature, as the reaction progresses, the temperature will continue rising, right? The temperature continues rising. Okay, so that's T. So you can see the effect of the progress of reaction on these variables, Ca, Cb, and temperature, from the beginning of the reaction to the conversion of interest, 0.65. Okay, so how these are how these variables, how the change in these variables will affect the rate of reaction. So again, x, so now we have minus Ra versus x, and again this x is 0, let's say this x is 0.4 and this is x 0.65. Now I'm gonna show you the effect of the change in concentration, only the change of concentration. If only the concentration was changing, then the rate of reaction will decrease, right? Will decrease. Let me plot it again. Okay, here we go. Okay, this is, oops. Okay, so this is the effect of the change in concentration only. Okay, so let's plot the effect of temperature only. So as the reaction progresses, the temperature increases, so that will cause the rate to increase. This is the effect of let me write it down, effect of change of temperature only. Okay, only. Okay, so therefore let's see who wins. So now let's plot, okay, the actual rate of reaction. So at the beginning the increase in temperature wins, so that means that the rate of reaction will increase. The rate of reaction will increase, and this will continue until 0.4. Okay, So the change, the increase in temperature is pulling the rate of reaction up, while the decrease in temperature, the change in concentration of is pulling the rate of reaction down. But who wins? Who wins? We said the rate of reaction, the temperature wins, and therefore it will increase the rate of reaction. Okay, but then who wins? Then the change in concentration wins. Okay, so the concentration of CA is very low, CB is very high, so the change in concentration, which pulls again the rate of reaction down, okay, will win. So it will pull the rate of, let me use the same color, it will pull the rate of reaction down. Okay, it will pull the reaction down, although the temperature is trying to pull the rate of reaction up, but its effect is not as much. Okay, so who wins here? We said the change in concentration wins, and therefore the rate of reaction will reduce. Okay, enough for this explanation. طيب. This reaction was carried out on an industrial scale, adiabatically, and in the liquid phase in the shown reactor scheme. For the specified conversions, x1.2, x2.6, x3.65, the entering, for the specified conversions, calculate the volume of each of the reactors in this scheme. The entering molar flow rate of N-butane was fixed at 50 kmol per hour. Okay, so what do we want? We want to calculate V1, V2, and V3. How? From the kinetic data given, which is minus RA versus minus RA versus X. Okay, that's the kinetic data that we have. Okay, how do we find these volumes? By using the design equation. And you know, in the design equation, who appears? Minus RA or 1 over minus RA? Well, basically 1 over minus RA. And precisely if A naught over minus RA. Can I use if A naught for the whole reactors? For all the 3 reactors? Yes, I can, because we have reactors in series with no side stream. So all my calculations are based on the feed to the first reactor. So that means I should really add a third row to make my calculations easier, which is FA naught over minus RA. Okay, so can you do this? Can you calculate V1, V2, and V3? Okay, this is the solution. How you get it, we can discuss it a little bit. So I assume that you have already solved this problem and you have already found the volumes of the reactor. Just make sure that you got it right. So for the first reactor, the volume was V1 times FA naught divided by minus RA1 times X1, where X1 is 0.2, right? And minus RA is evaluated at 0.2, or FA naught over minus RA was the one here. Okay, then we went to the second reactor, which is black flow reactor. So the integration of FA naught over minus RA dx evaluated from 0.2, which is x1, to x2, which is 0.6. So there we go. It's from 0.2 to 0.6. So you have 3 points. As you can see, you can use the Simpson 1/3 rule. Okay, and you can use these, as I said, these 3 points. Therefore, you will use these 3 points for the function of FA naught over minus RA. And finally, you have the CSTR, the CSTR, where we have the V3. V3 equals FA naught, again all calculation based on FA naught here, because reactor in series with no side reactions. So V3 equal FA naught over minus RA3 times X3, right? X3 minus X2. Okay, what is X3? Well, X3 is this guy, right? And X2 is this guy, as you can see here. But this guy is evaluated at X3. So which one you're gonna take? Which FA naught over minus RA3 you're gonna take? Well, it is this one, right? Okay, excellent shabab, excellent. Right, this is the areas, or these are the areas which represent the volume of each reactor. The first one is CSTR, right? The second one is plug flow reactor. So the first one is the area of a rectangle. The second one is the area under the curve, plug flow reactor, and the last one is the area of a rectangle, because again it's CSTR. طيب, now let's go to another topic, comparing the CSTR and plug flow reactor volumes and reactor sequencing. So let's inspect the Liquid-Phase plot for the discussed adiabatic process. Let's compare the volume for CSTR with the volume of plug flow reactor for the conversion ranges of, here we have 0 to 0.2. So from 0 to 0.2, which volume would be less? Well, you guessed it right. The volume of a CSTR is less than volume of plug flow reactor, right? Just by comparing the area. Okay, from 0.2 to 0.6, well, if you use CSTR, then the volume will be larger, right? The volume will be larger. Okay, and you don't want to do this, right? Okay, so use plug flow reactor. So the volume of CSTR would be bigger than the volume of plug flow reactor. What about for the conversion from 0.6 to 0.65? Sorry, that is there. 0.6 to 0.65, that is here. Okay, here again, you can see that if you use plug flow reactor, the volume will be smaller. So the volume of CSTR is greater than volume of plug flow reactor. But see here, remember we said the volume of CSTR is usually larger than the volume of plug flow reactor for isothermal reactions. But this is not an isothermal reaction. This is a reaction which is operated adiabatically. Therefore, the temperature is not constant. And we can see that the volume of CSTR would be less than the volume of plug flow reactor. So, lucky us that we put the CSTR first, right? Okay. I have another question. Is there a better arrangement that would lead to a smaller V total? Is there a better arrangement? Okay, so should we use, remember in this example, we used 2 CSTRs, right? And 1 plug flow reactor. Is there, and we put CSTR, right? We put CSTR, and then we put plug flow reactor, right? And then we put another CSTR. Is there a better arrangement? Do we need to use 2 CSTRs and 1 plug flow reactor, and this has to be the arrangement, or is there a better way? Well, looking at the Liquid-Phase plot, if you want to achieve a conversion of 0.65, then there's a better arrangement. What if we use a CSTR, right, which takes you to a conversion of 0.4, and then use a plug flow reactor which takes you to the conversion of 0.65. So in this arrangement, we have less number of reactors. Instead of 3, we only need 2. Okay, and we should start with a CSTR. That will give me conversion of 0.4. That is a better arrangement where the V total is less, even the number of reactors is less. But one would say, how do I make sure that my CSTR will take me to 0.4 and then my plug flow reactor will take me to 0.65? How do you make sure? Well, it's not a trial and error, it's not a magic. You design it, right? You design it. So for the CSTR, okay, the CSTR, okay, you know that design equation is this times x1. So you know that you want x1 to be 0.4, okay, and therefore you design the reactor. You design mean you make the volume, as the needed volume. So you use the correct needed volume in order for the conversion to take you to 0.4. The same thing with the plug flow reactor. Okay, when you design Fa naught over minus Ra dx, okay, you know that start with 0.4. You want to make it take you to 0.65 conversion, so you calculate the volume, and when you calculate it, you design it as I said, and then you build the reactor and you operate it, okay, at these conditions, adiabatically obviously here, and it will give you the desired conversion. Okay, great. So this will lead us to questions regarding sequencing of reactors. Which reactor should go first, then which? Okay, which type of reactor? And of course, if they're choosing the reactor, the question will be what its volume should be. Right. In the sequencing of reactors, where the desired overall conversion is specified. So we specified our overall conversion, our desired overall conversion is specified, 0.65 for instance. One is often asked, which reactor should go first to minimize the number and total reactor's volume? The answer is, it depends, right? It depends on the kinetics and the sequence, right? It depends on the shape of the Liquid-Phase plot and the relative reactor sizes. Okay, let's look at the same topic from different angle. In the sequencing of reactor, where the type, number, and volume of the reactors are specified. So, خلاص, we have ordered already the reactors. For example, one CSTR, one plug flow reactor. We know the numbers, 1 and 1. And the volumes are fixed. That's the reactors we have. I ordered it, now I have it here. Okay, and this is its volume. The question now is different. One is often asked, which reactor should go first to give the highest overall conversion? Remember, Shabab, when we have design, okay, so first we should have the kinetic and thermodynamic data, right? We should know the conditions. I'm going to operate this in. And then the question would be, if I know my desired conversion, then I calculate the required volume, right? So if I specify X, then I calculate V, right? However, if I already specify the volume, okay, that's the volume, then I need to calculate X. So in this case now, V is fixed. Now the question is, which reactor should go first to give the highest conversion, highest overall conversion? The answer is, again, it depends. It depends not only on the shape of the Liquid-Phase plot, but also on the relative reactor sizes. Okay, so suppose you were given a Liquid-Phase plot and 3 reactors along with their volumes. So we said, okay, you have now these 3 reactors. 2 of them is CSTR, 1 of them is plug flow reactor, and the volume of each of these reactors is given. And ask to find the highest possible conversion. The highest possible conversion. So what would you do? Would it be different? So if I put CSTR, then again CSTR, and then plug flow reactor, would it give me the same exact conversion if I put plug flow reactor first and then CSTR, CSTR? Or CSTR 1, no, and then plug flow reactor, and then CSTR 2. Or CSTR 2 first, and then plug flow reactor, and then CSTR 1. Or, think with me, or CSTR 2 and then CSTR 1 and then plug flow reactor, or plug flow reactor and then CSTR 2, CSTR 1. So see, you have lots of options. So let's talk about the number of possible arrangements. The number of possible arrangements. That would take you to a course that you have finished already last semester, okay, because it was a 200 level course, which is statistics, right, where you learned about permutation, tabadil, right, or combination, tawafiq, right? If you have permutation, so the order now is important. Is the order important in this case? The reactor? Yes, it is. Okay, so in our case, what's the number of possible arrangement? Well, it is a permutation problem. Okay, so let's see. Let's see for the first option. So we have 3 reactors, right? R1, R2, and R3. What are the possibilities that I have for reactor 1? Where it could be CSTR1, CSTR2, CSTR3. So we have 3 possibilities. What about for reactor 2? Now, I have only 2 possibilities because I have used already one for R1. It's like, taking a ball, okay, and you calculate its probabilities, right? And then you don't return this ball inside, right? So now the probability for the second withdrawal will be different, right? So here, for the second reactor, you have only 2 options, the other 2, right? What about the third reactor? Khalas, you have used already 2. You have only 1 option for the third. So in total, you have 6 possible arrangements. Okay, so suppose you were given a Liquid-Phase plot and 3 reactors along with their volumes and asked to find the highest possible conversion. Okay, how would you calculate X? How would you calculate X? Well, the methods we use to calculate reactor volumes all apply. You know the design equations. Except the procedure is reversed and a trial and error solution is needed to find the exit overall conversion from each reactor. What do we mean? Well, let's take an example. Let's say my first reactor is a CSTR, so I use the design of a design equation for CSTR, and we say this is V1, therefore this is X1, and this is evaluated at the exit of the first reactor. So the question now is, okay, do we have X1? Do we have X1? Well, we don't, right? Do we have V1? Yes, we have. We said it's the first CSTR. So here we go. We have the volume. But do we have X? If we don't have X, that means you cannot tell what is the value of this as well, right? Because the rate of reaction depends on X, because X affects the concentration. Okay, so what do? We assume, right? We assume a value for X1. When you assume a value of X1, then you can find this value of A0 over minus RA1, right? And then you multiply this by this and calculate V1. And then you compare the V1 calculated to the V1 actual. If V1 calculated is more than V1 actual, okay, so the required calculated volume is more, that means your assumption of X1 was very high, right? Okay, so what do? You assume another value of X1, another value which should be less, correct? So now you assume again, assume now x1, which is less than the previous one. Okay, so for instance, if here you assumed x was point, let's say 3, here you assume x is 0.2, and now you do the calculation again. From this you find the corresponding FA naught over minus RA, and then you again multiply the new x1 with the new FA naught over minus RA, and you find V1 calculated. Now again you compare V1 calculated to V1 actual. If V1 calculated in this time was less, the required volume was less than the actual volume, that means you assumed a small x1. So you again go ahead and assume, right? So again you can assume x1 in this type somewhere should be somewhere between 0.2 and 0.3, let's say 0.25, and you do the calculation again and you compare. Okay, so it's a trial and error solution, and you can find the solution in Blackboard for such a problem. Okay, similar problem. So please follow that and solve it by your own. Okay, so with this we reach the end of segment 1. See you soon in segment 2 of lecture 9.